3 of our talk about generalized functions, and at last we come to this concept. We consider a special set of C0 infinity, what consists of, I forgot to tell what omega is some domain in Rd. And this set consists of all functions what are finite in omega, and secondly they have any number of derivatives. So any derivatives of this function can be computed. And this derivative is continuous function. Let us write it by words. Let's draw several examples. Once again, omega is beam 0 to infinity, and something what is infinitely smooth, and starting from some point it is equal to 0. So support of this function is closure of this support is a finite set in omega. And it can be easily proved what this space is vector 1. So we can define pointwise addition and multiplication by number, and all actions of vector space are fulfilled. And we can define convergence in this vector space. Very special kind of convergence. So we say what sequence phi n converges to limit function phi in D, so we call it D convergence. If first any derivative of phi uniformly converge to corresponding derivative of limit, so uniform convergence, if you forget, means what supremum of all axis in omega, absolute value of difference phi n minus derivative of phi goes to 0, then n goes to infinity. So it means this. And another requirement is we need to have special compact set in omega such what all supports of phi n belong to this set. No? We can say even causal support. So for all numbers, all indices supports of all functions in these sequences, they belong to some given compact set K. So in this case, we say that sequence phi n deconverges to function pi. The set of vector space of C0 infinity equipped with this D convergence gives us so-called space of test functions. This space consists of best possible functions, so not only infinitely many times differentiable, but also finite in omega, and also equipped with very strong convergence. So it's very tough requirements, and I don't know, more strong convergence, and it's called T from omega space of test functions. I have to admit what this space with this convergence doesn't correspond to any normed space. So we cannot build a norm such what convergence in this space coincides with D convergence. We even cannot build a metric. So it's topological space. We can build a special topology, but we will not do it here. We just consider convergence. Okay. if we have a vector space, we can consider functionals on this space and can consider linearity of these functionals. So, and if we have convergence, we have continuity of this function. We can introduce continuity of these functions. So we can define d star on omega as a dual or adjoint space to D, space of all functionals. Traditionally, it was introduced by Laurent Schwartz with functionals called by letter T. T, all functionals defined on space of test functions. T of alpha 1 phi 1 plus alpha 2 phi 2 is equal to alpha 1 t phi 1 plus alpha 2 t phi 2. So linearity of this functional and another continuity of this functional. So t of phi n converges to t of phi for any phi n of d converges to phi. So if all these requirements are fulfilled, our functional belongs to this space of D star. This space is called elements of this space called generalized functions. Or Laurent Schwartz called them distributions. Both these terms are in use now. First question, why do we call these strange objects functions? So what connections do these elements of dual space to some topologic space of test functions, what relations does it have to functions, to rules, what correspond elements of one set to elements of another set? And let's consider this question. Let us have some function what is defined on omega and what corresponds some real numbers to elements from omega. And let's f is so-called locally summable. On What is it? So it's summable on any compact subset of omega. So F is summable on K of any compact subset of omega. This summability is can be understood in terms of Riemann integral or better Lebesgue integral. Look, for example, in our example of omega of this beam from 0 to infinity, function 1 divided to x, hyperbolic function, surely it is not summable. But it is locally summable because on each compact subset it is bounded and continuous, so it's obviously summable. So, of course, these locally summable functions, they can be discontinuous and any imaginable functions belongs to this class. So it's a very wide class of functions. And let us consider we take and fix such function f, and let us consider the distribution of generalized function defined on phi as an integral over omega of f multiplied to phi for each phi from space of test functions. Of course, it is functional because for any phi it corresponds some number. So Tf is functional defined on space of test function. It corresponds some finite number because if we consider this functional, this integral, phi is equal to 0 everywhere outside the support, closure of support, and on this set phi is summable, and f is summable, and phi is obviously bounded, so the product is also summable. So yeah, it is corresponds some given real number for any argument from set of test function. Also, it's obviously linear functional because integral is a linear operation, and also it is continuous because if f and d converge to phi n, sorry, deconverges to phi, then this deconvergence is more than enough to go to the limit with in the integral. So we have this. And it's exactly means continuity of our functional. So this this is indeed generalized functions, and important thing, what each locally summable function corresponds to some generalized function. And these distributions or generalized functions what are raised by some summable, locally summable functions, they called regular. There is some facts from function theory what we will use. Sorry, without proof. Author is German mathematician Paul Dubois-Reymond. And this lemma says what if f is locally summable on omega and integral of product of f to any test function is equal to 0, then f is equal to 0, strictly speaking, almost everywhere in omega. Because of this lemma, if we have two distributions raised by, so let's assume what f and g some locally summable function. And Tf and Tg are the same distribution, so they it's the same functionals for any argument they give the same result. Then, according to Tipler-Raymond lemma, we will have f minus g phi dx equal to 0 for each phi. So f is equal to g almost everywhere in omega. It means what correspondence between functions, locally summable functions in omega, and regular distributions is one-to-one correspondence. So each function corresponds to some regular distribution, and only one correspondent this function. So our set of generalized functions contain at least correspondence of every locally summable functions in omega. So all normal functions, what we considered from the beginning of studying of mathematical analysis, have some correspondence in our set of functionals on space of test functions. So the regular distributions, we can say they correspond to ordinary functions as we used to. But there are also some other representatives in the set of distributions. And let's consider such example. We define T delta from phi as phi from 0 for any phi from T omega. We assume what 0 belongs to omega. If it's not, everything is very simple, it will be 0 distribution. So, it's very easy to prove that it is indeed generalized function. So it is indeed linear continuous functional of phi. I will not do it. You can do it easily. Let's assume what there is some function f locally summable such what T omega is equal to distribution raised by this function. Let's define omega dash as a difference between omega and one point set 0. So if we have omega and point 0, so omega dash will be all points of omega except this one. Well, it's easily can be proved what it is open. So if we take phi from C 0 infinity on this omega dash, then phi from 0 is obviously 0, because it is non-zero only on, or can be non-zero only on omega dash. Then our T delta from phi is phi from 0, and if phi belongs to this space, it is 0. So means what we have this, and by Jabbar-Riemann lemma, it means what f equal to 0 on almost everywhere in omega dash. But omega is omega dash plus just 1 point. So f is also equal to 0 on omega. Also almost everywhere. T delta from phi should be equal to 0 for all phi from C 0 infinity on omega, because f is 0 almost everywhere. But obviously we can find finite functions what are not equal to 0. So our distribution is not doesn't correspond to any summable function, and such distributions are called singular. And this particular distribution is called, maybe you already understood, delta functions of Dirac. So the same function what we considered in the very beginning. Let's make a small break.